Welcome back to Linear Algebra. I'm Dr. Jeff Groh. Today, we're going to talk about eigenvalues and eigenvectors. Where does this word eigen come from? This is a German or Dutch word, and it sometimes is interpreted to mean proper, but also sometimes it just means same. When you multiply a vector on the left by a matrix, that matrix gives you another vector. Often you might start with some vector x and end up with some different vector y, perhaps rotated through some angle and dilated or contracted. If the matrix leaves the vector in the same direction, some constant times x, and it's customary to use the lowercase Greek letter lambda. The uppercase looks like this. It's L-A-M-B-D-A. If the matrix leaves the vector in the same direction, then that's kind of special. So we're going to give that a name. Let A be a square matrix so that it is n by n. We say that lambda is an eigenvalue of A with corresponding eigenvector V if, first of all, V is not permitted to be the zero vector, and AV equals lambda V. So the matrix A preserves the direction of the vector V, but perhaps not the length. Lambda will be either a dilation factor or a contraction factor. Note that if V is equal to the zero vector, then lambda could be anything. So we're not going to allow V to be the zero vector and still be an eigenvector. Eigenvectors are non-zero. The applications for eigenvalues are all over the place. We use them for solving systems of linear differential equations in our course in differential equations. We also use them in quantum theory. It turns out that the eigenvalues of the Schrödinger operator are the energy levels of a quantum system. Yes, these eigenvalues are going to be very important. So you need to study them and understand them very well. How do you find them? How do you solve AV equals lambda V for both lambda and V? Well, here's an idea. Suppose that we take lambda V and subtract it to the other side. That will give us the zero vector on the right. Now it may be tempting to factor the V out at this point, but A is a matrix, and lambda is just a real number, so you can't do that. But there is something you can do. You can insert the identity matrix. That means maybe you can factor the V out, because now you'll be subtracting a matrix minus a scalar times a matrix is still a matrix. So they're the same kind of thing. You can subtract it. Maybe we can factor the V out. Of course, you cannot factor V out on the left because matrix multiplication is not commutative. V times A minus lambda I with V on the left is a product that's not even defined. V has to be factored out on the right. Remember, v has to be a vector that's not the zero vector, which means we have a linear system, a homogeneous linear system, that has infinitely many solutions. It has to have a non-trivial solution, and therefore must have infinitely many solutions. That implies that the matrix A minus lambda I is singular, or the determinant of A minus lambda I is 0. In fact, it is exactly this equation that will permit us to find the eigenvalues. Once we know what the eigenvalues are, we'll go back here and find the eigenvectors. For example, suppose my matrix A is 0, -2, 3, 5. What are the eigenvalues? And find some corresponding eigenvectors. Step 1. We're going to solve the determinant of A minus lambda I equals 0. Remember, A minus lambda I is singular when lambda is an eigenvalue. So the determinant will be 0 if we have the right choice of lambda. But we don't know what lambda is yet. So what we'll do is we'll calculate the determinant of A minus lambda I. Lambda I, we have the determinant of 0, -2, 3, 5, minus lambda times the identity matrix, 1, 0, 0, 1. Now, that means we subtract lambda from the diagonal elements of the matrix A. We'll have minus lambda, -2, 3, and 5 minus lambda. This will always give us a polynomial. A determinant consists of a finite number of products and sums of the entries in a matrix. A finite number of products and sums of entries in a matrix with a variable like lambda will give us a polynomial. You always get a polynomial of degree 2 if the matrix is 2 by 2. If the matrix is n by n, you'll obtain a polynomial of degree n. Here we get minus lambda times 5 minus lambda, and then minus -6. This gives us the equation 0 equals a positive lambda squared, a minus 5 lambda, and a plus 6. Here we have a quadratic equation. I want you to be experts at solving every quadratic equation. You're going to be able to use the quadratic formula, you're going to be able to factor these, whatever it takes. You need to know how to solve quadratic equations. Every year, students struggle, no matter how far along in their training, calculus 3, differential equations, linear algebra, solving quadratic equations, which you learned how to do in Algebra 1. I'm on your case about this. Solve these correctly. Now notice we get a plus here. That means this factors with 2 minus signs because we have a minus in this slot. So it's going to be lambda, lambda, minus, minus. Factors of 6. Well, they're 1 and 6 or 2 and 3. In this case, it has to be 2 and 3 in order to combine and give us -5. We deduce then by the zero product theorem. The zero product theorem says that if you have two things multiplied together that give you 0, a zero product, then either the first factor is 0 or the second factor is 0. In this case, if the first factor is 0, lambda is equal to 2. If the second factor is 0, lambda is equal to 3. We now have a complete list of the eigenvalues of this matrix. What we need to do next is step 2, find the eigenvectors. In step 2, for each lambda, you have to solve the system of equations A minus lambda IV equals 0. Let's start with lambda equals 2. With lambda equals 2, we are subtracting 2 from the diagonal elements of this matrix. We'll have -2, -2, 3, 3. We're solving for v. The right-hand sides are 0, 0. So I'll put this into an augmented array. You can see right now that the rows are going to be dependent. If we take 3 halves times the first row and add to the second row, we end up with a row of zeros. We can then multiply the first row through by -1/2, yielding the reduced row echelon form 1, 1, 0, 0, 0, 0. If our eigenvector has coordinates x, y, we deduce then that x plus y is equal to 0. This has solution y equals minus x. So our eigenvectors will all be of the form x minus x, or in other words, x times 1, -1 for arbitrary values of x, as long as x is not 0. Because if x is 0, you get the 0 vector, and then it's no longer an eigenvector. We could have figured this out just by looking at the reduced row echelon form. If my reduced row echelon form is of the form AB 0, 0, 0, 0, then this corresponds to the equation AX plus BY equals 0. It turns out our eigenvectors are going to be any scalar multiple then of B -A. Switch these two and negate. If I plug in B first and then -A for Y, I definitely get a solution. So from this spot, I reverse those two and negate 1. Every scalar multiple of that will be an eigenvector. I'll describe something called an eigenspace. It's denoted by e with a subscript of lambda, where lambda is whichever eigenvalue you're dealing with, is the set of all v such that AV is lambda v. And this includes v equals 0. The eigenspace is a subspace of Rn, whatever n you're working with, in this case R2. So in this example, E2 will be the set of all t times 1, -1, such that t is a real number. It describes all of the eigenvectors and the 0 vector thrown in for good measure in order to make it a subspace. We need to do the same thing for lambda equals 3. We'll start by subtracting 3 from the diagonal elements, and then setting the right-hand sides equal to 0. Note that you always are able to reduce, in the 2 by 2 case, immediately one of the rows to 0. By elementary row operations, row 1 plus row 2 gives you all zeros on that second row, so you may as well just cross it out. We now know the eigenspace E3 will look like the set of L t times switch and negate 1 to -3, such that t is an element of the set of real numbers. In fluid dynamics, the gradient of the fluxes gives you a matrix, and turns out that the eigenvalues of that matrix are the sound speeds. Applications are all over the place for these eigenvalues. So one more thing I want to talk about here in this particular example. We had 1, -1 as an eigenvector. This gives us a line. Every vector on that line, when multiplied by the matrix A, will double in size, dilates by 2. We also had 2, -3. That gives us another line. Every vector on this direction gets tripled in size. Other vectors won't be just dilated, they'll also be rotated. For example, if I take 0, -2, 3, 5, and multiply by the vector 1, 0, what I'll get is 0 and then 3. That's actually rotated through 90 degrees and dilated by a factor of 3. There are some special cases that you need to be aware of. Suppose I have the matrix A, and the matrix A is a diagonal matrix like this one. What are the eigenvalues in this case? Remember, step 1 is to solve this polynomial equation, the determinant of A minus lambda I, which is obtained by subtracting lambda from the diagonal elements. This equation, by the way, is called the characteristic equation. In this case, the characteristic equation is particularly simple. It's 2 minus lambda, 3 minus lambda, which immediately implies that the eigenvalues are 2 and 3, the diagonal elements. That's not a coincidence. Anytime you have a diagonal matrix, you can tell what the eigenvalues are because they're sitting right there on the diagonal. That means, for a diagonal matrix, you don't need to do this step. Just jump right down to here and write down what the eigenvalues are. Step 2, let's find those eigenvectors. For lambda equals 2, we subtract 2 from the diagonal elements. If our eigenvectors are of the form x, y, then this tells us y is 0, but it leaves no constraint on x at all. That means the eigenvectors are of the form x times 1, 0, where y is 0, x is anything. That means the eigenspace, E2, is the set of all t times 1, 0, such that t is an element of the set of real numbers. For lambda equals 3, we subtract 3 from the diagonal elements. And this one tells us that x is 0, and y is unconstrained. So our eigenspace will be the set of all t times 0, 1, such that t is a real number. In yet another example, suppose our matrix A is 2, 1, 0, 3. This kind of matrix is called upper triangular because everything below the main diagonal is 0. Is there something special here? On our step 1, we solve the characteristic equation. 0 is the determinant of the matrix with lambda subtracted from the diagonals. We obtain again 2 minus lambda, 3 minus lambda, and then minus 0. So once again, the eigenvalues are sitting right there on the main diagonal. It follows then, if lambda is equal to 2, in our second step, we subtract 2 from the diagonal elements. These are dependent rows. One can be reduced to just a row of zeros, and we end up with y equals 0. So our eigenspace E2 is the set of all t times 1, 0, such that t is an element of the set of real numbers, picking off that 2. For lambda equals 3, we obtain -1, 1, 0, 0. Switching and negating, we see that the eigenspace is the set of all t times 1, 1, such that t is an element of the set of real numbers. Switch and negate one of them. I need to make formal some definitions that we made. Given some n by n matrix, A is an element of the set of n by n matrices. The characteristic polynomial of A is the determinant of A minus lambda I. The characteristic equation is 0 equals the determinant of A minus lambda I. An equation must have an equal sign. If it doesn't have an equal sign, it's not an equation. An equation is two expressions separated by an equal sign. We have the following theorem. If A is a diagonal matrix, upper triangular, or lower triangular, then the diagonal elements of A are the eigenvalues. In our next example, suppose the matrix A is 3, 1, negative 1, 1. Let's find the eigenvalues and the eigenvectors. So step 1. Write down the characteristic equation. 0 is the determinant, 3 minus lambda, 1, negative 1, 1 minus lambda. That gives us 3 minus lambda times 1 minus lambda minus a negative 1. We'll get a positive lambda squared minus 4 lambda plus 3 plus 1 is plus 4, and that obviously factors as lambda minus 2, quantity squared. Now I want you to see something. We get lambda equals 2, but lambda minus 2 appears as a factor of the characteristic equation twice. We say that lambda is 2 with algebraic multiplicity equal to 2. We'll make a formal definition of what we mean by algebraic multiplicity after this example. On step 2, we find the eigenvectors. And to do that, we subtract 2 from the diagonal elements. We get an eigenspace, E2, it's the set of all t times 1, negative 1, such that t is an element of the set of real numbers. Now I want you to notice something. The dimension of this eigenspace, since it only goes in one direction, is 1. A basis for the eigenspace is the vector 1, negative 1. The dimension of the eigenspace is 1. The algebraic multiplicity was 2. The dimension of the eigenspace is called the geometric multiplicity. Let lambda naught be an eigenvalue of some matrix A, which is square, n by n. The highest power, k, such that lambda minus lambda naught to the power k is a factor of the characteristic polynomial is called the algebraic multiplicity of the eigenvalue lambda naught. The dimension of the eigenspace is the geometric multiplicity. Here's an example you should be aware of as well. Suppose our matrix is diagonal, so we see that lambda equals 2. The algebraic multiplicity will also be 2, which I think you can see pretty quickly. What is the geometric multiplicity in this case? So this is our step 1. Let's move on to step 2 and find the eigenvectors. For that, we have to subtract the eigenvalue from the diagonal elements, and we obtain this. Everything's 0. What does that mean? It means there are no constraints on the coordinates x and y. Whatever your eigenvector is, x and y are independently choosable. That means your vector v can be expressed as x times 1, 0 plus y times 0, 1. These are going to be your eigenvectors. Your eigenspace, E2, is the set of all s times 1, 0 plus t times 0, 1, such that s and t are real numbers. That means a basis for the eigenspace will consist of 1, 0 and 0, 1. It follows then that the geometric multiplicity, the dimension of the eigenspace, is 2. In this case, the algebraic multiplicity and the geometric multiplicity are equal. In the last example, the geometric multiplicity was 1, while the algebraic multiplicity was 2. I'll state a theorem, but leave it for an upper division course in linear algebra to prove that the algebraic multiplicity is always greater than or equal to the geometric multiplicity. We've been finding eigenvalues for matrices. Eigenvalues do exist for linear operators. Suppose L maps V into V. It's a linear operator. We say that lambda, which could be a complex number, is an eigenvalue of L with corresponding eigenvector V, which is not permitted to be the 0 vector, if L of V is lambda times V. So once again, L does not change the direction of the vector, only some scaling factor, lambda. As an example, suppose L maps the infinitely differentiable functions into the infinitely differentiable functions and is defined by L of f is f prime. What are the eigenvalues and corresponding eigenvectors? Step 1. We need to solve L of f is lambda f. In other words, we need to solve f prime is lambda f. We might even call this y prime equals lambda y. What functions have derivatives equal to a constant times themselves? You can see that y is any constant times e to the lambda x would work, because its derivative by the chain rule would be lambda c e to the lambda x, which is lambda times y. You can see then that the eigenvalues are arbitrary numbers in the set of complex numbers, with the corresponding eigenvectors being functions of the form scalar multiples of e to the lambda x. Suppose that again we have L, which maps infinitely differentiable functions into infinitely differentiable functions, and L of f is f double prime. What are the eigenvalues now? Now we're looking for functions that have second order derivatives that are constants times themselves. Try this. Suppose f of x is of the form e to the m times x. Then f prime of x is m e to the mx, and f double prime of x is m squared e to the mx. So if a function of this form satisfies this equation for the eigenvalues, then we have m squared e to the mx equals lambda times e to the mx. That implies then that lambda is equal to m squared. What values of m will work? We get lambda equals m squared, where m is any complex number.